So even if we ignored serial correlation, this is what we'd end up with. If we correct for it using any of these three procedures, we're not really deviating too far from our ordinary least squares. But we've done what we're supposed to do. So it's one of those afflictions that in the end you don't really make that big of a difference. But it's something you almost have to account for. You should account for. And it's one of those things that you're likely to be asked about on a job interview, for example, where how do you control for serial correlation? And if you can just throw out terms like, I would use a Cochrane-Orcutt or Praise-Winston or Hildreth loop, then you'd be fine. And again, they're simple commands, but they are different than ordinary least squares, and it's going to be a different command here. Instead of reg, it's going to be a different command. So it's pretty simple. So what is serial correlation? The errors are correlated with themselves over time. They don't affect the coefficients that much. As we can see, they do affect the standard errors. And the standard errors are, so those are all t-stats. So what we can see, because remember the coefficient of x here, 14.75, and the corrected errors are, what is that, almost twice, more than twice, 37? I erased it. Remember the bigger error is going to deflate your t. So even though these are still statistically significant, they're even more significant when we've corrected for serial correlation. Yeah. This is one of the things you just have to cover. It's kind of a drag. All right. Imposing structure on lag coefficients. We did the Allman lag. And we almost all got it? Almost? What do you think your problem was?
I put it aside and went back to it a couple days later, and it just screwed me all up.
Yeah. Then it was just a bunch of, then it looked like
Yeah, a
this.
mess, pretty much.
Yeah. It is, what do you call it? Kind of housekeeping. You just have to be kind of neat and tidy with stuff. Kind of like the stuff we're going to do today.
I think that's the only problem I had was like leaving something really tiny out of my commands
Yeah.
and then having to like go back and redo it.
And if you notice in my do file, I made use of copy and paste a lot. Just put things on top of each other and just keep things kind of in a systematic fashion. Even and I tried to follow the PowerPoint, kind of set things up so that you see a pattern, and you can see that if you screwed up, there's going to be a deviation from the pattern. So 1, 2, 3, 4, 5, 6, 7, 8, and then this is 4 squared, 3 squared, 4 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So if you just kind of keep things tidy, you'll see where you make an error. And because sometimes your parabola won't come out parabola-ish, and you kind of figure out, okay, where'd my mistake go? And then you can see something, if you see a 1 here, 125 instead of 25. It's like, okay, boom, I can fix that pretty easily. And the only reason you're going to know that 125 doesn't belong here is because it's not following this pretty simple pattern. So nice and neatness with your do files. All right, infinitely distributed lags. So one of the problems with the Allman lag or the polynomial lag is that we had to, we're always going to use a second degree polynomial. We're always going to use a parabola. But we had to play with the lag structure. And we know that made a big difference, right? When we changed the lag structure from, what was the optimal one, 6? To whatever. the polynomial changed significantly. So again, we're stuck with those information criterias, and as I said before, they're a pain, but it's kind of like serial correlation. You have to use them to try to give us some structure on how many lags to include in the model. Believe it or not, infinitely distributed lags don't suffer from that because we're assuming that the lag structure goes on forever. So there's no question in how many lags do we include, which is nice, which is pretty cool. So the downside is we have to use this model. So this guy Coit developed this or used this model in, I guess was the first, is attributed this model in this 1954 text. In all honesty, he stole it from physics. He stole it from geometric decay, which I remember learning in chemistry, whatever class that was. So essentially he says that the lag coefficients, our betas, are going to follow this geometric decay of the order beta 0 times lambda to the I, where lambda is between 0 and 1, and I is the length of the lag. So literally, if we have, so what we're doing is we're going to have sales as a function of an infinite number of lags of advertising. So this is just going to go on forever. T minus 3, T minus 4, T minus 5, T minus 6, T minus infinity. It's literally an infinitely distributed lag. And then he says, okay, substitute our lag structure, beta I equals beta 0 times lambda to the I, into each coefficient. So again, I is the length of the lag. So here's, for no lags, this is beta 0 to 0, which is 1. So lambda goes to 1. This is beta 0 times lambda to the 1, beta 0 times lambda to the 2, beta 0 times lambda to the 3, and you do that forever, infinitely. But we can't estimate this. We've got an infinite number of lags. We'll get carpal tunnel syndrome typing that forever. I guess we'd never stop. Plus it has an infinite number of coefficients, so we'd run out of degrees of freedom. So here's this little trick he did. We're going to lag this model, the infinite lag, by 1 period and multiply it all through by lambda. So lag our infinitely distributed lag model by 1 period and multiply it all through by lambda. And we get this. So this is just S multiplied by lambda, lagged 1 period, and then we multiply everything times lambda. There's no time dimension to alpha, so we can't lag that. But everything else, we're lagging by 1 period. So notice that in our original sales equation, this is beta 0 times AT. It's now lambda times beta 0 times AT minus 1. And then everything else is lagged by 1 more period.
What's lambda?
Lambda is our decay coefficient from up there. It's just a little mathematical trick he did. Then he does this. He subtracts this from this. Which he conveniently calls the Coit transformation. So that's ST. He subtracts ST minus 1. And if you look closely, if you subtract these two things, you're going to get alpha minus lambda alpha, which we can treat as alpha times 1 minus lambda. And then everything else is going to cancel out. So what's going to cancel out? Here's lambda beta 0 AT minus 1, lambda beta 0 AT minus 1. So these cancel because we're subtracting. These cancel. these cancel. Everything else is going to cancel out except for this stuff. The stuff that remains is going to be the constants, beta 0, at minus 1, and this term here, which looks a lot like, what does it look like? Does that look like this? Except replace this with lambda. Yeah, it's the error term and a 1 period lag of the error term. So we got this on the right side, so move that over. And we end up with this. So we moved lagged sales over onto this side. And we've got this error term ut minus lambda ut minus 1, which would essentially, so if there, so let's write this out. So serial correlation exists when we have ut equals lambda ut minus 1 plus et. All right, so this is serial correlation. After we've gone through the quick transformation, we end up with this term here. So this term would be, if we just solved for ut, I'm sorry, et, it would be ut minus 1, which would give us that term, right? And this is not serial correlation. Excuse me. So, I get excited about this stuff. So the quick transformation actually eliminates serial correlation if it exists in the model, which is actually pretty cool. But the other thing is, that we end up with what we're going to call the lingering effects model. That's what we're going to estimate. It turns out that this model, which is up there, is going to be our lingering effects model, where lambda is our carryover effect. It's how much of previous advertising is carried over into the next period. 1 minus lambda is the opposite, which is the rate of decay. And the impact multiplier is the effect of advertising. So beta 0 is going to be the short run effect of a unit change in advertising. So beta 0 is that initial effect of advertising. How much does advertising impact sales today? That's beta 0. And then in the long run, we can calculate the intermediate impact multipliers as beta 0 plus beta 0 lambda, because remember, lambda is how much of advertising is carried over from the last period. And then that's in period t plus 2. And then 2 periods down the line, it's going to be lambda plus beta times beta 0 plus beta 0 lambda squared. And we can calculate that for any number of periods. So this tells us, again, the impact of advertising today, tomorrow, and 2 days from now. And it's going to decay at that rate lambda. Remember, lambda is between 0 and 1. The long run multiplier is, if you do a Taylor expansion, it's just going to be beta 0 over 1 minus lambda. Right. This is why we had to go through that. I know I burned through it, but the Praise-Winston procedure of correcting for serial correlation and the Cochran-Orcutt procedure for correcting for serial correlation don't work if we have a lagged dependent variable in the model. So we can't use either of these two. We're going to have to use that third one, which is the Hildreth-Lou procedure. All right, so here's our model. Here's some of the other cool stuff. The mean lag on average, how long is advertising lasting, is lambda over 1 minus lambda. The median lag is the log of 2 over the log of lambda, the negative log of 2 over the negative log of lambda. Those will be pretty close to each other. Again, this is an infinite period lag, so it goes on forever theoretically. So we calculate these duration intervals. So define P as the proportion of the total cumulative effect of advertising that is realized after m periods. So P equals 1 minus lambda to the m period. We solve for m. So get lambda by itself. How do we solve for this thing up in the top? One way is to take the log of both sides. And we've got m times the log of lambda times the log of 1 minus p. And then divide both sides by log of lambda, and we got m. So what does this tell us? It tells us what percent of the advertising effect is realized after m periods. Subject to duration, interval bias, we'll talk about that also. So here's a lambda, here's the lag coefficients of a lambda equal to 0.25. Remember, lambda is how much is carried over in the following periods. In this case, lambda, only 25% of it is carried over in the next period. So you get this decay occurs pretty fast, and then it approaches 0 and goes on forever. It's asymptotic to the axis. Here's the lambda of 0.5. More of the advertising effect is carried over in the next periods, so the decay is going to be slower and advertising is going to last longer. The effects of advertising are going to last longer. Here is a lambda of 0.75, and again you see a similar pattern. So, a common duration interval in the marketing industry is the 90% duration interval. So, how long does it take for 90% of the effects of advertising to decay? For us to exhaust 90% of the effects of advertising? Because remember, it goes on technically forever. We can, keep increasing the number of periods. So, with a lambda of 0.25, the 90% duration interval tells us that 90% of advertising is going to be realized after 1.6 months, or years, or weeks, or whatever it is. With the 50% duration, with the 50% lambda, then the 90% duration interval is going to be 3.32 months, or periods, or whatever it is. So advertising is going to last 3.32 periods. If you've got a lambda of 0.75, then your 90% duration interval is going to be 8 periods. So what you can see is, with the lambda of 0.25, 90% of the effects of advertising is realized after 1.6 or so periods. After that, it gets smaller and smaller and smaller. With the lambda of 0.5, 90% is realized after 3.3, so about there. And then with a lambda of 0.75, 90% is realized after 8 periods. So the bigger the lambda, the more of the effect of advertising is carried over into the next period, the longer the effect advertising is going to have. So think of it as, again, we're modeling how much we remember of a firm's advertising effects. Does this make sense? So this is a little bit different than the parabola. The parabola, we're saying that the effects of advertising can grow over time and then start to die out over time. Here we're saying there's an initial impact and then that effect decays over time. So it really depends on how we think, not necessarily how we think advertising is going to, the effect of advertising is going to be, but what we see from the unrestricted advertising lags, the unrestricted lags. Is this making sense? Yeah. This is a really cool model. Yeah, we got that. Larger the lambda, the more it's carried over. Yeah, we got that. And the longer the effects of advertising, the longer the 90% duration. All right, issues with the lingering effects model. Yeah, it's going to ignore this stuff. Adding flexibility. Here's the cool thing about the lingering effects model. If we add a lagged value of x, so if we think, if we think that the largest effect of advertising isn't going to be in that first period, it might be in the subsequent period. If we think that that peak effect occurs not in the first period, which the picture tells us, but in subsequent periods, we can change that peak. So instead of looking like this, we can change that peak. So here's first period, second, third, fourth, and so on. If we think, for example, there's going to be some build-up effect. So if we think that the biggest effect might be in the second period, then adding lagged advertising will allow that to happen, and then this will decay. Again, like that, which is pretty cool. So here you just add lagged advertising, and it's still the same lingering effects model, except we're going to switch the peak over. Beta 0 is still the short-run impact. Our lambda beta 0 plus beta 1 times lambda to the I represents the lagged effect in period t minus I. That's a mouthful. For example, in the first period, we're going to get this carrier effect here. This is going to be lambda to the 1. Second period, same thing, but lambda to the 2. Third period, you get the idea. Lambda to the 4. we think that the peak effect might be in the third period, then we're going to add another lag. Oh, yeah, that's a long one. Okay. So now we're going to add 2-period lagged advertising. And the coefficients are going to follow this lag structure. And again, trying to look at the pattern. And this is how you want to do your do files. You can see that initial impact is still going to be beta 0. 1 period later, it's going to be lambda times beta 0 plus beta 1. 2 periods later, it's going to be lambda times beta 0 plus beta 1 times lambda plus beta 2. 3 periods later, it's going to be lambda beta 0 plus beta 1 times lambda plus beta 2 times lambda. That's 3 periods. 4 periods later, it's going to be that lambda squared. 5 periods, it'll be lambda cubed. 6 period lambda to the 4th power, and so on. So once we see this pattern repeating, then it's pretty easy to graph those coefficients. And with these lag effects go on technically forever. So the key to graphing these things is having this snapshot right here. This is how we're going to write, this is how we're going to graph those lag coefficients. We need to pull lambda from our regression, pull beta 0 from our regression, pull beta 1 from our regression, and then beta 2. But then after that, it's just a mathematical pattern that we have to follow. So more of the same. All right. If we add 3, then we're going to get the same thing. And our lag structure will look something like that. So what this allows us to do is construct a different picture of the effect of advertising. So let's take our polynomial. Is always going to look like a polynomial. It's always going to look like that. Kind of builds up gradually and then kind of dies out gradually. That makes sense. But even if we think that that happens, it also might make sense to say, oh, yeah, I think the peak effect is in that same period. Let's call this 5 periods. But I think it's going to go up, and then it's going to decay geometrically like that over time. So it lets us model a similar behavior, but with a different kind of decaying structure, where this is going to be a lot more of an abrupt decrease in the effect of advertising as opposed to a gradual decrease in the effect of advertising. It all depends on those unstructured lags. What does the picture of those unstructured lag coefficients look like? That's going to guide us to how we want to model these, which one of these models we want to use. So kind of the pure lingering effects model is basically that. Initial effect, and then it starts to decay. But we can add some flexibility and add it to gradually increase, to increase quickly, and then start to die off in that same decaying structure. Yeah. We'll have to look at those unstructured lag coefficients to see which ones makes the most sense. So, what do we want here? Adding more lag values. All right, so let's see how we can implement this. So really, the implementation is pretty easy. We'll start with the pure. That's our lingering effects model. So we're going to regress sales on advertising and lag to sales. That's it. Everything else is structuring those lag coefficients. So it's a much simpler model. There's no information criteria. We have to come up with how many lags do we include. There's no, there's no issues in that. The only thing we need to worry about is graphing those coefficients. But it's pretty simple, right? Initial impact is beta 0, and then the subsequent impact is first, after one period, it's beta 0 plus beta 0 lambda, and then so on, and so on, and so on. So that's the structure of our coefficients. All right. This data's not on this computer, so. What's the score? That's where I came back.
Wait, you guys had it back there the whole time? How dare you?
You're not sharing.
No, it's rude. You need to turn on the sound.
SAS. I don't want to use SAS. 6.3. What's the score?
8-17.
Cardinals?
No, Cowboys.
The Cowboys are ahead?
Surprising. Be so weird.
All right.
Deja vu.